Okay, thanks everyone for coming to another new session of ONEPAS. Today, we're happy to start the thematic session on the mathematics of thin structures, which has been graciously curated by Irene Fonseca from CMU. And well, as you can see, she'll start off today with the lecture of the same name. So let's hand it over to Irene.
Okay, so thank you, Ian, and also the organizer of ONEPAS for this opportunity. It's been interesting to prepare this. So, so what I'll try to do today is to give you an overview from my perspective, and also biased by my own trajectory in this subject, of what we know and where we are today in the analysis of this subject, which is basically the following. So you have a material which is a 3D material with some properties, with some energies, and you let some of the dimensions, for example, the thickness go to 0, and so in the end you end up with a thin structure, say 2D structure, and the question is, how are the properties inherited at the level of the 2D structure from the properties at the level of the bulk? So, by the way, the date here, it's not, of course, today's date. It's because it was the last time I edited this slide. Okay, so let me first tell you. So this is basically what I was saying. So you have a structure. Think about it in these terms. So it's a very simple cartoon. I'm going to call it omega epsilon, and I'm going to try to be consistent throughout. So omega epsilon is basically you have a cross section, which is this little omega cross 0, and you have thickness epsilon over 2 above x3 equal to 0, and thickness epsilon over 2 also down there. So that's what I call omega epsilon. The middle plate is this little omega, which is a nice bounded Lipschitz domain. And you start with the bulk energy. So again, this is going to get maybe a little bit more involved, but say, grosso modo, imagine that you're dealing with, say, a nonlinear elastic material. So this is the energy for each domain omega epsilon. This is your preferred bulk energy density. Well, actually, usually it's non-negative, right? So it's not just R, but should be 0 to plus infinity. And as the thickness goes to 0, omega epsilon approaches the cross section. And then the question is, where do the energies go, right? Well, you could also think in terms of 3D, 1D, for example. You could have both, say, the x1 and the x2 collapse, and you'd have like a string or a rod, etc. But that's not what I'm going to talk about today. But there's also the 3D, 1D dimension reduction. But here I'm going to focus on 3D, 2D. So it's just the thickness that's going to collapse. Now, if you just leave it like that, you won't see anything. This goes to 0. Okay. So you have to rescale in some way. And different scales give rise to different theories. So if you scale by epsilon, which is the thickness of your sample, this is going to lead you to membrane theory. If this looks like epsilon squared, you're going to have plate theory. And if you have an epsilon to the 4th, it's going to be von Kármán theory. Most of what I'm going to say, it's going to be within this first regime, the membrane theory, with one exception, but most of it is going to be membrane theory. So here is the program, which has been announced by the ONEPAS organizers, but just to remind you, next time around it will be Gilles, who's going to take from what I'm going to talk about membrane to other regimes. So that's his title, Beyond Membranes. Then Marta Levica, she will talk about the geometry and morphogenesis, problems and prospects, followed by Giovanni Di Fratta, micromagnetics of curved-thin films, and Maria Giovanna Mora. She will talk about energy of Mobius strip. So again, here you're going to have also geometry involved in the problems. Jean-François Babadjan will talk about reduced models for linearly elastic films with fracture debonding. Actually, I'm going to talk about some of these also today. And Cyril, well, it's a surprise, we don't know yet. Okay, so let me then go a little bit of history here. So in terms of linear elasticity, and again, I'm talking in terms of the mathematics of, if you think about the physics and all that, there's a lot of literature out there. So I'm talking more in terms of the analysis. And that, grosso modo, it's calculus of variations, PDs, some geometrical measure theory. Okay. Within the realm of linear elasticity, you can go back to the 80s, the Stringent and C.R. Lee and others. Nonlinear elasticity started late 80s. Milke, so here you have a few names, Alberto Buttazzo Percivale, Fox Raoult and Simo, etc. And again, I'm not trying by any means to be exhaustive in the literature I'm providing. And so if your name is not there and it should be there, please forgive me. And then a big leap happened in 1995 with a paper by Ledre and Raoult in the membrane regime. So you take the energy I gave you, divide by the thickness. And it was using methods of basically gamma convergence. And that, as I write here, that opened a huge body of literature on these dimension reduction problems with different flavors. So you could have now your bodies has some micromagnetism in there, or you're addressing say a mixture of two materials, and at the same time that you are compressing them to the middle plate. So now you're going to have basically a merging of optimal design and dimension reduction. And what if you allow for fracture, right? So that's brittle thin films. And what if you have composite materials, right? And with smaller and smaller cells. So that's homogenization. And the list goes on. So, and the program that I mentioned to you before, many of these talks are going to address several of these bullets that I have here. And I'm going to today try to address basically most of them, okay? And again, forgive me, but I'm going to do it through my perspective and also through some of the work that I've done on that. So that is the membrane theory. Bending theory for plates and shells, that was now work of Fonseca, James, and Mueller. So now that's much later on, early 2000s, and then Fonseca, James, Moore, and Mueller. And then the von Kármán theory, again, open a whole body of new literature. There is a so-called rigidity estimates, which now are ubiquitous in most of this work. And that's Fonseca, James, and Mueller. And as I say, stay tuned for Gilles' talk. He's going to talk a lot about that. But as I said, what I want to talk about today is a 3D to D dimension reduction in nonlinear elasticity. And there are many, many contributions. I have a list of names here. And again, your name may be in there. Apologies. But the list goes on. It's huge. Okay. So let me see if I can set the stage here in a way that as I go through my talk, this is going to be a constant. So even every time that I change to homogenization or this or that, I'll try to use always the same framework with the same notation. And disclaimer, most of what I'm going to say, although I claim is for nonlinear elasticity, it's not. And why it's not? Because in nonlinear elasticity, these conditions, we know it's fundamental, right? It's non-interpenetration of matter. Your energy should explode when the Jacobian, when the determinant goes to zero. And so in particular, you cannot allow for, say, polynomial growth of your energy because it fails, right? And a lot of what I'm going to say uses these. There will be one part where we'll actually be genuinely working on elasticity, but that will be basically at the end of my talk. But anyway, most of what I'm going to say violates this. Okay, so let's start with Raoult, and let me revisit that because that was the starting point of all this analysis. So again, let me remind you, this is your domain, a thin domain, right? Thickness epsilon, middle plate, little omega. That's your energy. Your function V sub all F, say, I'll keep it between bigger than 1 because for p equal to 1, it's a completely different ball game, right? You're going to end up in BV and all that. I don't want to go there. So let's keep it in the sub all F setting. And what I'm going to do is, well, it's not very nice to work with variational problems where the domain is moving on you, right? So what do? You change variables so that you work on a fixed domain. And so that is the way you do it, right? So you rescale. But and so when you do that, and when you define the new variable from the V, you go to U, well, of course, the first two partial derivatives stay the same, but the last one comes scaled with a 1 over epsilon, right? So then this derivative now has an epsilon in there. So when you plug it into when you plug it here, so here's the so as I said, I scaled by epsilon. That's that. Change variables, right? So when I change variables, this epsilon goes away with the Jacobian, right? And now you get something that looks more like an order 1, but then this gradient is exactly the gradient of my new function u, except I have a price to pay, which is this 1 over epsilon, right? That's just change of variables, okay? And I use often this notation where primes stand for the first two components. So for example, x prime will be x1, x2. Grad prime is just the first two derivatives. These would be grad prime. I write a matrix 3 by 3 with a C prime, so 2 columns, and the last one C3, which plays a different role, right? Because of this 1 over epsilon. So I kind of singled that out with that bar, right? So that's the third component, okay? And by the way, of course, our deformations go from R3 to R3. You could do these from Rn to Rd, okay? So I'm not too attached to the 3, but it's just because in our minds, this was the beginning was elasticity 3 and 3, but it could be N and D, okay? And the theorem of Raoult says that, so again, you start with a continuous function, suppose it has linear growth. Again, you are in trouble here if this goes to infinity with the determinant, right? Because you could not have this hypothesis here. And they proved then, so the new energies, which are called F epsilon, so these are the rescaled energies. The F epsilons gamma converge, and I have a very short slide to remind you of what that means, but basically it's the relaxed energy of the system to one where basically you integrate now over the middle plane, and your function u, I'm going to tell you in a moment what that is. So you only see the first two derivatives of u, and the function u, the limiting functions u, well, they live here, but basically they don't depend on x3. The derivative with respect to x3 is 0. So when you collapse to omega, it's almost like the function u goes from little omega to R3. You lost one variable. And you're going to see why. Again, so let me tell you what this is. First, I should tell you what is W bar. So now C prime is going to be a matrix with 2 columns, right, and 3 rows. And it's just defined as you augment it with an arbitrary third row, you take the EF over that. That's W bar. And then what is Q of W bar? That is so-called quasi-convexification, which is that you take the unit cube on the plane, well, it's the unit square, and then you take all possible perturbations of this matrix with gradients of functions which go from this square into R3 and which have compact support. So basically you're looking at all possible gradients, strains of deformations which look like C prime X X prime on the boundary, because you're killing the boundary here with the C. And as I said, your limiting space is just going to be, you're going to lose one derivative. And by the way, as I said, this is not compatible with this. So, but we now know how to do that in other, in particular for von Kármán, and again, stay to Gilles, to his talk, because he's going to address that. So what is the roadmap to prove a theorem like this? The roadmap usually follows these 3 bullets. First, you prove compactness. That is, you prove that if you have a sequence UN with bounded energies, then up to a subsequence, they converge in some sense to some limiting field, right? So here you do the usual stuff. For example, you can subtract the average, right? This is just the average. You subtract the average and you prove it goes to some U, and then hopefully the U is going to live in the right limiting space, which is the one where you lost one variable. And you have convergence in some sense. So weak convergence in LP. So it's basically W and P weak convergence, right? And this is just because you want to use some kind of Poincaré or something like that, right? Okay, so that is compactness. And then is prove the gamma limit if and the gamma limit sup. That's the recovering sequence, is the gamma limit sup. Let me first go over the compactness, and you're going to see that in one slide we are done. So you assume that you have a sequence. Oh, this should be UN, I'm sorry, that it's uniformly bounded. But remember that W was coercive from below, right? So you had a bound where W, basically from below, you have the gradient to power P, right? Okay, so that means that, so if I plug that in there, this is what I get. This is now bounded in LP, right? That's the bound from below. Oh, but that tells in particular that this business better go to 0, right? Because it's multiplied by 1 over epsilon to some power. So on the other hand, by Poincaré's inequality, you have this inequality here. So this is bounded in W and P, right? Therefore, we know that up to a subsequence, it's going to go somewhere. So in particular, we have reconvergence of the third derivatives, but this is telling you that it better go actually strongly to 0. So that means that this one has to be 0, and you're done, right? So you prove that your U is in the right space. So that's just Christivity, and the fact that you have this, that 1 over epsilon. For the gamma limit inf, okay, so now you have a UN that goes to U. U now is admissible, lives in the right space V, and you want to prove that whenever UN goes to U, that the limit inf is bounded from below by that integral of the quasi-convexification, etc. And again, you can do that in one slide. And okay, so without loss of generality, you may assume that your limit if is a lim, just extract the subsequence. And then what do you do? So, okay, so then this is the limit. On the other hand, remember that the W bar was obtained by the W bar minimizing over anything that you put here, right? That was my W bar, which was up there. Okay, so in particular, I go down this way with W bar. The quasi-convex envelope, by definition, is always below the function. So that's, you go down, right? But it's also known that this quasi-convex envelope is sequentially weakly lower semicontinuous with respect to weak convergence. Therefore, you go down again. From here, you go down to this, right? So semi-continuous. But remember, this now does not depend on X3. This was omega cross minus a half. So the integration on x3 is 1, and this is the same as writing this. You don't have an x3 variable there. That's that. For the recovery sequence, well, so now you want to prove, so if I define this object like so, I want to prove that that's below this, my candidate for the gamma limit. And actually it's easy to prove that it's enough to show that it's below the function without the q, simply because this is lower semi-continuous, so you cannot go any lower. Okay, so the way you do it is, first you prove that this is actually, that this object is again lower semi-continuous with respect to strong conversing LP. Then if you prove this, you get that in particular, this is below this object. But we know that having conversing LP or reconversing W and P in this setting is the same because of the bounds you have. But it's exactly, that's a theorem in calculus of variations, that when you do this, what you get is the quasi-convex envelope. Okay, so yeah.
So which step will break down if you impose interpenetration?
All so far, because I'm using all the time that this business has a P growth from above. It's very important. For example, if I want to prove that this is a measure, for example, with respect to the domain of integration, I do that by combining, approximating sequences, and then proving that the error that I make when I do this combination is controlled. And I do that by using the upper bound.
Okay.
That's window. Okay.
Thanks.
Okay, so let me now just say, for the recovery sequence, again, remember that it's enough to prove that if I define this object, that's below this one. If I'm done with this, then I'm okay. Then sticking here the Q is easy. And for that, what you do is you use a measurable selection criterion that says, remember that what was this? This was, let me write, this was an inf of W of grad prime of UN of X prime with respect to some X3, C3, right? So that means that this is obtained for, this is achieved on columns which depend on X prime. They better depend in a measurable way. So there is this very fine measurable selection criteria that says, actually, you can do that. And you can find a measurable function such that this is actually obtained in this way. So the C here is actually is obtained as something measurable. Okay, fine. You do all that, and then you just introduce, and then you have an ansatz, which you say that, okay, so my approximating sequence is going to be the original U, depending just on X prime, and then I'm going to get this H, I'm going to multiply by, and I'm missing an X3 here. Well, okay, doesn't matter. And then when you do that, whoops, well, you can see it here. Well, okay. I have to I should put in X3, X3. Okay, but when you do that, you write what this is, you get exactly, you recover your energy, and then, but again, there's no dependence on X3 here. You see, there's only X primes. So writing this or writing this is the same. And this was exactly your starting point. So that was a double bar. So basically, just look at the definition and just make sure that the third column that you put in there is something which is measurable. That's Luderhout. And that was basically the beginning of this. And then comes work by Joy and James in 1997, where it's a dimensional reduction, but now it's within the context of micromagnetics. So again, and membrane theory. So again, you have the 1 over epsilon in there. And now you have a field M bar. This is going to be an isotropic energy that favors the easy axis. It's this, which basically could be like multiple well energy. And then, so this is the usual exchange energy, and this is the magnetostatic energy, which basically the field H bar and the M bar are related through Maxwell's in this way. And normally also you assume that M bar has norm 1, so or some norm which is fixed. Okay, so this has a name. The gradient of this H bar is called the magnetic field. So we have Maxwell's equations that are satisfied, which is the curl should be 0. And you ask the same question. So this is set on a domain whose thickness is going to go to 0. So what is the limiting energy? You're going to follow the same idea, change variables like so, change the last twice that you stretched so that it has now thickness 1. Rescale, again, I'm going to call F epsilon the new rescaled energy, and same thing as before, right? So you're going to pick up a 1 for epsilon here. The phi remains the same, right? Just change variables. And again, here, you're going to have the same now rescaled for the gradients. And again, and so now this just stands for the derivative with respect to x3, right? So you have here the divergence 2 by 2, and now this is the third with respect to x3, but you have a scale that appears in there. And you can prove that you have compactness, and you can prove that the gamma limit that you obtain is, again, you're going to lose the dependence on x3, and you're going to pick up something which looked very similar. So the exchange energy is basically the same, just with 2 derivatives. This is the same. And then here, this is now the new term that's going to appear, which is a very interesting term that appears out of this analysis. I am adding here some other references for other papers, some of them more recent, like in particular this one in 2018 of Cyril and some other collaborators within the micromagnetics framework. Okay, now let me move on to optimal design. So, and here I'm going to
quickly ask a question.
Sure.
Yeah, so the constraint on the gamma limit there, just if I could, the constraint on the magnetization, just how does that interact with the potential phi of m?
No, there's no interaction. You can do this with or without. It's just that the analysis becomes a lot more complicated, right? Because right, because if you want to work, say, always with fields that live on the sphere, right? You cannot truncate, you cannot glue things together and expect to stay on the sphere. So you have to keep projecting things back onto the sphere. And so the analysis becomes more complicated, but you don't see it really appearing here.
Okay, super.
Okay. So let me then, again, here I'm going to follow my work with Gilles on this. And so now again, so here you have, so you have, so if I want to make a picture here, so if this is, say, little omega, which is the cross section, and you're going to have here patches of, say, W1, and on the complement, so you put W2, and I'm going to consider I have cylindrical inclusions. You see that here, I'm going to assume cylindrical shapes, right? I'm going to assume that I only vary from one energy density W1 to another one W2, depending on X prime. So you have these cylindrical inclusions, right? And here, I'm going to assume that the volume fraction is fixed. So the amount of W1 or the amount of W2 that I have is the same. And then if you want to look at the compliance is defined as such. And the best design is the one that minimizes the compliance. So it should be minus, another way of writing is minus the sup of minus C epsilon, which leads you to basically the sup of an if. Again, membrane theory, I'm scaling by 1 over epsilon. You may assume that your field are 0 on the lateral boundary. All is same volume fraction. We don't know how to do this. It's a sup of an if. We know how to do an if of an if. So you know what? We are not going to find the best design. You're going to find the worst design. And so now you're going to have an if, both on the design, which is the chi that tells you where you're putting W1s and W2s, plus a deformation, right? So you have an if now on 2 fields, right? So if you're mising over all these, with this constraint that I want to have always the same amount of W1s or W2s. Again, you rescale, as you've done before. And no surprise, you get the 1 over epsilon appearing there. And again, we need this growth, okay, for what you've done. And we prove that we have a formula for the gamma limit. And the gamma limit, I don't expect you to read through all that, but basically it's going to look a little bit the same, right? You're going to end up with a variational problem just on the midplane, omega. You're going to have now a volume fraction which could live between 0 and 1. So that basically tells that mass is fixed. And then, and that's going to tell you how you switch from a W1 to a W2. Okay, the formulas are all here. I don't expect you to read it, but it's basically, it's explicit, if you wish, with self-formulas, okay? But we know how to do that. I should also say that at the end of the day, you still have an if human problem, because you still have an if over all possible thetas that do this for you, right? While before, the gamma limit, there was no if. You end up with an energy of something, right? So say for example, in the case of micromagnetics, there are no ifs here, right? It is what it is. It's an integral of something. Here, you're still trailing behind an if. Okay. And again, I'm giving here some other references for more recent work, but again, the literature on this is more complete than what I'm having here. And now let me talk about brittle thin films, and this is going back to work with Andrea Bredes, and so here we are allowing for a crack. So I'm going to assume that my field V is smooth outside a crack K, which I assume has dimension 2, right? So Hausdorff measure to finite. And so outside K, I have my usual W, and I can penalize the opening of the crack, which is the traces of V on each side, right? V plus minus V minus, the amplitude of the jump. And this is the normal to the crack, okay? Same thing, change variables. And then this is what you're going to have. So good news, omega stays fixed, but now of course, K now is going to vary, right? So now you get a K epsilon, which is fine. Again, the same 1 over epsilon there. And when you change variables, you will see that, okay, it's just the opening. The new primes stay the same, but the third component is now multiplied by 1 over epsilon. That's just change of variables, okay? Now, this smells a lot like Mumford Chart, right? So where you have, which is a completely different area because it's for image segmentation, but basically it's within the topic of free discontinuity problems where you have smooth functions away from cracks or from jumps, and then you end up with trying to minimize both on where you put the crack and the minimization of your field U. So this goes back, so again, that's Manfred Shah, goes back to the George and Ambrosio, and the formulation is in the space of special functions of bounded variation. If you never heard about it, I don't have time here to go over that, but basically what happens is that instead of having a pair of cracks and deformations, you just work with deformations, but you allow them to jump. And so you identify this crack with where U jumps. And so by doing that, and again, changing variables, you get something which now looks like so. And writing omega or writing omega minus the jump is the same because it has Lebesgue measure, it has volume measure 0. And then I now have the jump, and actually this should be the normal to the jump. Okay, I think I'm gonna skip all these about BV and SPV, but you're going to see that you're going to get the slides, so then if you want to go back, you can refresh your memory. Again, some other references on these, some in 2019, 2017, also Babajan and some of his collaborators are here, and again, other people have been involved. But then the bottom line is same type of hypothesis. You start with the same kind of growth condition. Your surface energy theta satisfies the usual hypothesis for this kind of variational problems. You should think of it as being homogeneous of degree 1, because normally it's given to you on just on depending on the normal, right? But then you have to extend, and you extend it like homogeneous of degree 1. It has some parity and some type of growth, but these are very classical hypotheses. And then when you relax, you find what you expect, namely the bulk energy is familiar to us now. It goes back to Leverrier-Haupt, and then you just have to work a little bit to find out what happens now to the surface energy. And there's a formula for that, where as it was the quasi-convex envelope, this is now what it's called the BV elliptic envelope, which goes back to Ambrosio and Breides, which is the equivalent of quasi-convexification for surface energies. I don't expect you to read what the formulas are, but basically what I want to tell is that we know how it looks like. Okay. Now let me also talk a little bit of debonding on thin films, and again, Babajan, Jean-François Babajan is going to talk about some of these in his new developments in his talk. So now this is the work with Kaushik Bhattacharya and Gilles Frankfort. And here what we have is something a little different. So I'm going to call omega epsilon minus the bottom part of my sample, omega epsilon plus the upper part of my sample. And I'm going to have two different energies in W1 for the upper part, which I call W1, and one for the bottom part, which I call W2. Again, my V is allowed to jump, and I'm going to have a penalization of the jump. This square V means just the jump of V across omega. But you have to look at it as being the traces. You're going to have a Sobolev function on top, a Sobolev function on the bottom. And so you're going to have a trace of V coming from the top, a trace coming from the bottom, and this is just the difference between the traces. And again, they satisfy the same kind of boundary conditions, change variables, same stuff, right? And here, okay, by the way, I started here with the sum epsilon to some alpha positive. You do your change of variables. We know this looks like that, this looks like this, and now this one is going to look like so. You lose one alpha because of the change of variables. And of course, depending on what alpha is, you're going to have different answers. So if alpha is less than 1, you're going to find that, let's see, you're going to see that the targets, so in terms of compactness, are functions which only live on the middle plane. And then depending on different conditions you're going to, on phi, like subadditivity, you're going to prove that you can prove in an abstract way that your gamma limit is something that can be written like that. But the question is, what is f? I know it has an integral representation, but if I don't tell you how little f looks like, it's not very useful, right? And so there are different formulas for f. I don't expect you to read through these. It's pretty messy. Look at these. It's really messy, but we know how it looks like at the end of the day. So there's a recipe to compute these new integrand, depending on what you see. This W here reflects what W1 and W2 look like. Now, depending on X3, because if it's X3 positive, it's one thing, X3 negative is another, but it's basically well known, and you can see that, for example, in this regime, you get something which is again familiar, right? It's your QW1 bar and then the QW2 bar. This is for the regime alpha less than 1. There are two other regimes, and very briefly, if alpha is more than 1, so you have targets which look like so. If alpha is equal to 1, so this is what I mentioned before, if alpha is equal to 1, this is what you get. And if alpha is bigger than 1, then you have a decoupled model. So this one is coupling what's happening, and he's completely decoupled. You just have something happening for the top and something happening for the bottom. And again, here I refer to Babajan, Jean-François Babajan, and now for paper 2016. I will now move to bending moment in membrane theory. You remember that W has a perceivity of order P, right? From below. So in particular, this business is bounded in LP, which that's why it forces this one to go to 0. But if I look at this as a whole, a 1 over epsilon du dx3, that's bounded in LP. So you may ask, so where does it go, right? So that's what we're going to try to do. So I'm going to write this as, that's going to be the bending moment, B is for bending. Same time of hypothesis. And again, V is our familiar space where you have no choice. This is going to disappear in the end, du dx3. Okay, but now I would like to know that not only I want to know what happens when U epsilon goes to some U that lives in the right space V, but I want to look at this quantity and try to find out what is in terms of this B bar. So what is the energy that's captured by the bending moment? So now your targets are pairs. Is the U that does not depend on X3, and there's this B bar. And again, you look at the gamma limit when these are the targets, and you prove that, well, it's not quite just the Q of the W bar as before, but it's going to be something else that depends again on the first two derivatives of U, but now on this field B bar. And this is going to be, this is going to be the if over, well, actually this should be here. So when the phi's are periodic, so on the first two variables, this is the way you compute this new field now, okay? So this lambda just stands for the fact that you're going to have this 1 over epsilon that is playing in front of the derivative. So again, it's essentially explicit. And I don't expect you to remember all this, but I'm just giving you basically a menu of different versions of basically the same problem, and you layer on top of it other questions. Let's now look at homogenization. So again, I'm going back to my work with Andrea Brides and Gilles Frankfurt. So now suppose that this function, it's not just a W, but is actually a family of functions, and that they depend on epsilon. For example, you could have homogenization, right? Where, for example, what I have here would be a W of, say, y prime over epsilon, y3, and blah. So here in this work, I'm just going to let the homogenization happen on the middle plate. This can be done more generally than that, okay? But let's just concentrate on this, that I'm just having this one oscillate. I change variables. So this one remains the same, because remember that I change variables only on the third one that picks up the 1 over epsilon here. And you prove that, yes, I know how it looks like. It's going to look like an homogenization. The U lives in usual space, no dependence on X3. This is the W, the new W, the effective W is a W ohm. It has a formula, it's a limit of a certain function G. And the function G, for those of you who are familiar with homogenization, it's the usual type of form. You have bigger and bigger cells, and you average over the bigger cells with functions, yes, functions that are 0 on the lateral bond. Again, in homogenization, there is a huge literature, and I'm giving just some of those listed here. Okay, let me see if I now move really fast. I had a couple of things I still want to talk to you about. Remember that I said that most of what I'm going to say is membrane. That means you scale by 1 over epsilon, just the thickness, with one exception, and that's the exception. So this work with Laura Bufford, who was my PhD student, Elisa Davoli, when she was my postdoc at CMU. And so now here what we do is you're going to scale by epsilon squared, okay? And so when you do that, you now pick an extra 1 over epsilon in front, right? I have a 1 epsilon, and still this is the same, right? And so what we did was homogenization here, also just depending on, I'm just homogenizing on the middle plate, but actually I even allow for 2 scales, having it at 2 scales. You could do it at multiple scales. But the point here is, so before you didn't have that one. Now I'm putting another one, but you could even put others. But the point is now I have an extra 1 over epsilon in front because I'm dividing by epsilon squared. And that's going to lead you to plate theory. Okay, and so there are different regimes. There's this regime where, and then you can ask, okay, so you have 2 phenomena here. You have the plate and you have the homogenization. And you may ask, well, which one goes first, right? So again, you have 3 possible regimes, or actually you have several regimes, but, and I am listing them here. And here, I'm assuming that I have non-degeneracy, that's the usual hypothesis as say Fonseca, James Mueller. I'm assuming that I have frame indifference, and I'm assuming that I have this condition. So now this is realistic. Okay, so now this is physically reasonable. There's still one regime that it's open, which is this one. Again, I don't have time to go over that, but the bottom line is that now we are getting close to having hypotheses which are physical. And so again, this is our hypothesis, right? And at the end of the day, you're going to have, okay, so there's a compactness result, which is what I'm writing here. And at the end of the day, we are going to find a target, which is, I wrote it here. Again, I don't expect you to remember what this, but basically we know what these look like. It's going to be a quadratic formula. It's horrible, as you can see. But again, if you're familiar with Fonseca, James Mueller, this is familiar, or with the work of Maria Giovanna, this is familiar. There's these usual formulas that you expect, basically, if you develop into this formula up to second order. And I keep it here just for the record because you're going to have these on record. But anyway, but we know how to do that. So finally, I want to now wrap up with work which is going on. It's right now, we don't have it written yet, with Elisa Davoli and my current PhD student, Liquid Kennedy. So what we are doing here is now high contrast homogenization in membrane theory. So what we have is that, so the blue things inside here, so these will be soft inclusions. So again, it's an homogenization, except I have two materials, and one is stiff, which is the red, which is basically the matrix. And inside the matrix, I have these soft inclusions, okay? In particular, could be air, could be or vacuum, okay? And so this is what you have, right? That's what I have here. Again, so you're going to rescale, right? So you have that. And so, well, didn't rescale yet, but in omega epsilon, again, you have some energy. If you are, so chi is going to be 1 in the blue, right? So outside the blue, so when chi is 0, you are on the red. When chi is 1, you are on the soft inclusion, you have the blue, and because it's soft, you can have a huge strain there, basically, right? You can afford, because I'm multiplying by epsilon. So I can afford a huge strain there, okay? Because this compensates. And now this is going to be physically reasonable and acceptable. So from below, we accept, we impose a condition like that, which is innocuous. I'm going to assume that yes, indeed, you have non-interpretability. So the energy will explode if the determinant is 0 or below 0. I can assume that from above, I have some type of polynomial growth, but again, it will explode as the determinant gets close to 0, right? So you see that there's this one depends there. And a prototype could be something like that. Okay, that's very familiar. And I'm going to assume in particular that these are the growth conditions on the soft part. And our result is going to use the notion of two-scale convergence. This is going back to Allaire and Brian. So I just remind you what two-scale convergence means. So if you have a sequence U epsilon that lives in LP, we studied two-scale convergence to a field V that now picks up another variable, which is going to be basically the homogenization variable, if you have the following conditions. So when you multiply U epsilon with test functions which oscillate very fast on that variable, you now get fast variable. Okay, and we also say that that you have strong two-scale convergence if, in addition to this, the LP norms converge to the LP norm. And the theorem says that, okay, so this was the epsilon. You rescale as we did before, right? And what we prove is that you have strong convergence, strong two-scale convergence to now a W that is decoupled in the following way. U is basically the macroscopic variable, okay? That's what happens basically if you integrate on the fast variable, right? And then this is what sees the oscillations. So you're going to basically decouple the two. And the first part, well, this was the stiff part. That's Ledre-Raoult, basically, right? Plus homogenization, which I told you before how to do that, right? With the work with Briders. So this is familiar. That's the stiff part. And what is new is that now on the soft part, you're going to get now a formula which is written in terms of the two scale limit. And it's written in this way. And we know exactly how, okay, this is the one which I gave you before. So there's not, and this is just the usual Q2 bar of the Raoult. So you homogenize here, you don't homogenize there, right? Again, there are many other works on related subjects, and I have here some of the references. In particular, we used quite a bit these two references in what we are doing. Actually, we are still doing that. We are beginning to write it, but it's still work in progress. And I think it's a good place to stop. Thank you.
Very nice talk. Thank you very much, Irene. Are there questions or comments? Feel free to just unmute yourselves and ask away.
So Irene, beautiful talk. So in that last example with Lickett's work, so is also, so I guess something like a log of the determinant would also be covered in this example, no?
Well, let's see, we have, okay, so what we need, basically this is what we need. We need that we have this type of growth. 1 over the determinant, it should look like a 1 over the determinant to power less than 1.
Oh, okay. Oh, but it's still fine. I see.
So, so there are lots of open questions, and in particular, for example, there is work by John Ball on these stiff and hard problems, and actually his powers are not our powers, and so how you conciliate these, it's a different matter, and so there are many open questions on this still. But at least we now can handle these basically conditions like these, which are more palatable, because in most of the work that, except for the von Kármán, the plate thing, we, not the Kirchhoff, sorry. The time we had actually a constant, a universal constant. And that, of course, is not good, because you cannot allow the determinant to go to 0. Or better, we allow the determinant to go to 0 and nothing bad happens, right? So now we can do that. But there are still issues there that need to be understood in terms of the ranges and what are the right conditions. And this is being written as we speak, basically. So everything else that I talked about, it's out there. The papers are published and out there, except for this last slide, or last two slides.
I have a question, if you don't mind. So if I understood correctly, I think maybe all but one of these models have the reference configuration a perfect cylinder, right? So your big omega is little omega crossed with a flat interval, right? So yeah, my question is, is that important, or can you have the top be like a smooth function or something like that?
The right person to answer that is Marta. And probably in her talk, she will talk about that, because she's the expert on that. But let me first give you a very simple answer, which is, suppose that omega was like, little omega was not flat, could be like a surface, right? If it's not too bad, if it doesn't have folds and stuff, right? Basically, if it's diffeomorphic to a flat omega, and then you can have like, well, for example, let me just tell you something here, because this was, it was here. You see, in this work with their brothers and Jill Frankfurt, you see how our omega epsilon looks like? Looks like, okay, but here I have an omega which is flat, but you look at the profile. The profile is less than an epsilon times an F epsilon. I can put F epsilon like this. Until now, it was Y3 less than epsilon times epsilon, right? Right, until now, this was this was just a 1, right? Was actually divided by 2. But it doesn't have to be, right? And so our work is very general in that sense that we can have epsilon times something depends on x. So every time you take x prime, you could be at different heights. You see what I'm saying? But you have many more other geometries, and Marta and her collaborators have worked a lot on that, different geometries, and yes, that's a good question.
Actually, is the f epsilon in the energy functional the same as the upper graph, or are those the same?
No.
Okay, no. so like the one in the energy is like an external force or something like that. Yeah, okay.
It's a load. It's a load. So I noticed, you read these slides a billion times, and when you present, say, oh my God, so I already saw like 4 or 5 that I have to correct. But okay, no, these are loads. These are external loads. So these are not the same. This is just a profile.
Thanks. Anyone else? Stephen, you have your hand up. Go ahead.
Yeah, thanks. Lovely talking to you, Irene. A couple of questions. So could you say something about this BV elliptic envelope? Because you commented it was related to quasi-convection of surface energies. And sort of a related point, is there some interest in incorporating surface energies into these models as well?
I'm sorry?
Is there some interest in incorporating surface energy into these models too? So
absolutely. Yes. You could actually start with already surface energy, right? And to some extent, this was in there, right? Because this is a surface energy, what I have here, right? This is a surface energy. This is DH2, right? And so, okay, so if your W has linear equal to 1 growth, even if you don't start with surface energies, as you know, you're going to get them in the limit, right? This is the case where you have a P bigger than 1 growth with a surface energy. When that happens, and this has a P bigger than 1 growth, they decouple, they don't see each other. So you see that in the end, you have an energy that this just does the usual Raoult on the bulk, and then this has its own surface energy, but you don't see W's here, and you don't see thetas there, right? They decouple. Basically, you're relaxing the two separately. But so this is the case where I'm starting with bulk plus surface.
Yeah, so I guess I was looking for non-trivial coupling between the two.
For that, if you want to do that, these better have linear growth. If it has superlinear growth, they don't see each other.
And could you
that's a different ball game. That's a completely different ball game. Most of what I said is modified.
Yeah, could you quickly say something again about this BV elliptic envelope? Because you made this comment that was quasi-convection for surface energies.
Right. So what you do is let's see. So what you do is this. When you take, did I write it? Okay. So you have here by the way, this goes back to Ambrosio and Brides, where they have a whole collection of papers on the relaxation of just pure surface energies. You just start with surface energy, you end with surface energy, right? So it's a parallel to what we know in the classical calculus variations, where you start with bulk energies, right? And you relax and you get the quasi-convex envelope. So they've done the same thing. If now you just start with surface energies and end with surface energies, what is the envelope? The envelope is called the BV elliptic envelope, but it's the equivalent of that, surface to surface.
And with that problem, Irene, can you require it not to interpenetrate? Is that within the range of energies there?
In this one?
Yeah.
No. This is in the range where you're assuming that you have polynomial growth from above, which is bad. So the ranges where I know where you can do better again, are within the work of Marie Giovanna Mora, and Fonseca James Mueller. So Kirchhoff plates or von Kármán, and then I mean, like for example, what we are doing now with this high contrast homogenization, and there is quite a little bit of work by Hafs and Mandalena on problems where they basically assume that the right condition, that the energy explodes when the determinant goes to zero.
Okay, I wasn't talking about the bulk, I was talking about the crack. Is there anything to require the crack to only open up, or can the crack close and then?
Oh yeah, no. There's no, if you're thinking like, I don't know if you're thinking about like Frankfurt Marigot, right? That once it opens, it has to continue to open, right? There's no self-healing. No, we did not impose anything like that.
Okay, so in principle, the crack could close and then interpenetrate with itself.
Yeah, exactly.
Okay.
Exactly.
Okay, thanks.
Right. So yes. So you could have self-healing, which is not reasonable. Yeah.
Anything else? Okay, well, let's thank Irene again.
I have a few slides to correct, and when I correct them, I send you the PDF.
Okay, sure. Yeah.
PDFs?
We can, if you're willing to share, I'll happily put it on the ONEPAS website.
Okay, absolutely. But I need to correct a few things.
Sure. And as a reminder, everyone, we'll be back next week at this exact same time with a follow-up talk by Gilles Frankfurt. Hope to see you all then.